What we have for today, it's you will continue working in groups. I think it's, as I mentioned yesterday, the exercise set 3. It's very interesting. Okay, it's combining a lot of different things that you have already covered during the first 2 exercise set, which is to calculate production profile with time. You have to keep track of what's happening in the reservoir, what's happening with reservoir pressure, but also is including the complexity of the network, and it's not so simple, okay, because now the 2 templates can be producing differently, the rate will be differently, and you're also declining these 2 tanks, these 2 reservoirs in a different way, okay. And then the next complexity is the question number 2. Okay, the task number 2, when you want to evaluate using a subsea compressor at the towhead to prolong the plateau. For many, and that's what we mentioned before, for many applications, subsea applications, you use subsea boosting simply to prolong, to keep producing the same as you had produced before, or to increase. Okay, in this case, they are evaluating after the plateau is finishing to put a compressor there. Okay, so the first part is to calculate without the compressor how long is the plateau and how it starts to decline, and then the second part is to add the compressor. And for that is a bit tricky, so that's why you want to work on it in class, and then we take here like common questions, okay, such that we clarify a bit how to do it. So that's the plan for the first part, and then for the second part you have the second exercise, the second problem of that exercise set. Okay, it doesn't stop. You're always going to get exercise. Okay, but that's the way you learn, I hope. And in that part, I just need to clarify some of the equations you're going to use in VBA. Okay, that will be a separate field. Will be mainly using liquid Peregrino, and there you're going to look at this pump envelope. How is that changing? But for that we need a little bit more of theory to explain some of the equations we are using. Okay, so that's the plan, ambitious plan. Let's see if we manage to do it. Okay, but first let's do a very brief recap of what was done. So you want to produce from these 2. You are producing in plateau rate. So remember what I told you. If you have the rates that you want to produce, they came from some place. Okay, they came from God, they came from reservoir guy, reservoir expert, they came from someone. You should, the first thing you should make to make it intelligently, you fix the rate, right? I think I made a schematic here. You fix the rate, you come all the way to the wellhead. Your control element is here, is in each well. You don't have a choke for the whole template, you have a choke for each well. So you calculate the available pressure with the well rate here and here, and then you calculate the required pressure. You have the rates, you can go back calculate here, and then you compare. If that's positive, you don't have to do anything else. You don't have to run network, don't have to do anything else. Okay, you can continue to the next time step. If that gives you a negative number, that means the rate that you're producing is non-feasible, so you have to do network. Then you have to go to network. Okay. So the way we have structured the Excel sheet was you have one where you perform the time calculations, and in here you can also perform if available is greater than required. If that happens, you don't do anything else, you continue to the next time step. If in one time step you find that available is less than the required, okay, then you have to come to this sheet where you have to solve the network, the one that says task 1. And you have to think about it in real life. When you go to a company, you're going to work, these are 2 separate packages. Okay, one of them, this in data, will be probably a reservoir simulator where you compute things that happen with time, and this will be a production simulator or a network simulator. Okay, this might be Eclipse and this might be Gap. These are 2 separate programs. Now we are in Excel, we can deal with all of them in the same, and you can even think, well, I can try to integrate. Some students in the past, they have tried to put everything on the same sheet. Okay, and they have succeeded, but it's not so easy to explain. Okay, so that's why I prefer to keep them separately. So how do you find how much this constant rate that each one is producing? Okay, you might do it from reservoir studies. You run your reservoir model different times with different rates to see how is the drainage, which one achieves better recovery factor. But one strategy that is commonly used is splitting using the potential. Okay, and that potential you can use any kind of method to calculate. You can use a minimum bottom hole pressure, you can use a minimum wellhead pressure, you can include the whole system. In our case, we're going to include the whole system. Okay, just to try to see how much stronger or how much this guy can produce compared to this one. We run an open choke simulation, run no choke, a network simulation, and then we find out how much is this one compared to this one. Okay, and that's what we have done last class, open choke. Okay, and we see we can produce actually more, 22 million, and what I want is 10. Okay, so at least that makes sense that I can have some plateau for 10. Okay, but the most important, I see how much each template is producing. 14 from this 22, 15 are produced by template L, and 7 are produced by template M. So that's how I make the splitting. L is the strongest, the one that should produce the most, and M is the weakest, the one that should produce less. Okay, so that's how I make the splitting. And I'm going to keep that splitting, so I'm going to keep that rate, 6.7, and then 3.3. Where is 3.3? Here. Okay, for, we can put it even in red, because that's well, actually that's calculated. This is an input, this is also calculated, and I'm going to continue with that rate as long as possible. I'm going to try to produce that rate. Okay, and Marcus, he was saying which is very correct, in reality you have to change that splitting, how much each reservoir is producing, and you do that by the potential, because both reservoirs decline in a different way. Okay, it might be that, for example, let's say L, okay, produces a lot, has a lot of productivity, but the volume is very small. So after you produce a year, the pressure drops dramatically, okay, and then it cannot produce 15, but it can produce maybe 8, and the other can still produce 7. Okay, therefore then you should change to a splitting 50-50. Okay, but just to keep the complexity low, just to have like a warm startup, I just say keep that splitting constant. Okay, but that's what Marcus was suggesting. We do that potential calculation every time step. Then we find out that they might be, with time, they get tired, more quickly, which is the decline of the reservoir. Okay, so yeah, so I suggest you now with these rates you compute. Remember, we have to make from bottom hole to wellhead, and then I stop here, and then you have to start. My equilibrium point, it's actually here. Okay, it's here. I am doing it at the wellhead, so I'm coming all the way here, then I have to come all the way here, and then I have to compare. So just do that. Remember, you have to keep track of 2 reservoirs, so you have to keep separate the production of one and the other, how much you have produced from each one of them, and then see for how long you have the plateau. Okay, when is the plateau finishing? When one of these chokes, doesn't matter which template, gives you negative. Okay, when one of these chokes, either on this template or on this plate, gives you a negative number, that's the end of the plateau. Then that template cannot produce anymore the rate that I fixed, and then I have to lower it. Okay, so when all of you have reached to that point, we take another discussion to see how do we solve that, okay, in the network, because it's not so simple. You have in the network, you have one part where you have a fixed rate, but here you have a rate that you don't know, you have to calculate. Okay, so it's like half a network, half a constant rate. Okay, but let's say we give, let's say maybe 20 minutes. Okay, we take a discussion now, 10:50, and and discuss that issue. And I suggest you work in groups of 3. Okay? Good. Okay, so I have these 2 rates, right, that I found, 66.7, and then the other I provide the key of the field desired, and then simply make this is the total plateau of the field minus the template L. Okay, that gives me 3.3. Then I calculate the Q of the well, divided by 4. Okay. Look it. Okay, GP will be 0 at that point. Recovery factor simply this guy divided by this guy. The set is the C factor standing, that equation. And I have to use here the reservoir pressure, which will be there. Temperature is this one. Specific gravity of the gas is this one. And the unit was 2, right? I think. Okay, reservoir pressure is the initial reservoir pressure. This guy here. 95, makes sense, the numbers. Now I move with the rate that was given. I move to PWF. That's using the IPR equation. And I have to use, be careful, the rate of the well. Okay, so I have to use C, block it. I have to use N, block it. I have to use reservoir pressure. And I have to use the rate of the well. Okay, 216. Don't want too many decimal points. Then wellhead, that will be, I'm moving from the bottom all the way up, co-current, so it should be tubing P2, and then I have to say CT, it's this one, I think, tubing coefficient. You see here ID 6" is 7" tubing. Okay, it's a very big tubing. CT, that should be blocked. Then S, the elevation factor, that also should be blocked. Pressure at the inlet, that's the bottom hole pressure. And the rate, again, the rate of the well. Be careful. We are now moving on the well. Now I stop. Okay, I calculate from there all the way to the wellhead. Now I have to move backwards. So let's do that for for template M, exactly the same, divided by 3. Then GP will be 0, recovery factor will be this guy, divided by this guy. C will be this pressure, comma, this temperature, block it, comma. Many errors you have because you forget to block things, okay? So just you have to be very aware of that. Specific gravity of the gas, comma, and then 2. And then the pressure will be initial reservoir pressure. Okay, 92, again makes sense. PWF, I use IPR. And then that will be C. Here, block it. And I also block it. PR. And Q, the Q of the well. Okay? Yeah, the Q of well that is in M. Okay? Am I getting similar numbers that you got? Yeah? Okay. Now PWF, tubing, again, tubing P2. CT, block it. S, block it. Pressure and rate of the well, which is here. 153. Okay, and then now I have to go from the other side, from the separator to towel head, and then from towel head to template. So I calculate the Q of the field divided by 2. Good, because I have two flow lines. The towel head will be line P1 because I'm moving counter current. CFL, that's the flow line or the pipeline that it says here towel head to Gulfak C. That's where the separator is, and it doesn't matter which value you choose, they are the same. P2 will be separator pressure, which should be here. And sometimes they change separator pressure to get simply more production. Towards the end of the life of the field, sometimes they lower. It's a big issue. They have to make a lot of changes in the platform. But that's why we put it as a function of time. If later in life we want to change it, we are capable of doing it. QF, that gives you, yeah, that should be, this separator should be 60, block it, 68. Okay, and now we move. We are now at the towel head. We have to move two different paths. Okay, we have to move to the template M, which will be line P1 again. It's the same equation, horizontal flow line. CFL is the flow line from template to towel head. This guy here, they are slightly different. P2, it's P at the towel head, and the rate is the rate of the template. Okay, is the commingling of all, is this right here, 68. I don't need so many numbers. And I do the same for now this guy, line P1, resistance coefficient, that will be template L. Okay, did I take the proper one for M? Pressure will be pressure at the towel head, and the Q will be the Q of the template. Okay, let me check if I did it properly for this guy. Yeah. Okay, and finally the delta P of the choke will be the P available minus the template, 100 bar, and then here we have the available minus the required, will be similar to 85 bar. Okay, now comes the second, and it's, I just have to repeat exactly the same, but be careful. The main difference is the GP. Okay, GP will be the previous plus what I produced. I should take what was produced from the whole reservoir. Okay, so that's the Q of the template. That's this number times the difference in years, but you have to make consistent the units. This is in years, this is in days. Okay, so you have to multiply times the number of the days in a year. Okay, so it's the previous plus the what was produced in that year, and I should use also the same equation here, the previous plus the rate times this guy minus this guy times this guy. Okay, what else do I have to change? Do I have to be careful with? Reservoir pressure, right? First, the F now, I'm going to make it, that will be a function of the previous. Okay, remember that trick. We know the pressure changes very slowly from year to year, so we make it as a function of the previous, and we do the same here. We make it as a function of the previous, and now reservoir pressure is a function of how much has been produced. Okay, how much I take out of the tank. So I use that equation, M balance tank, and here is using, I have to compute the recovery factor, which will be very small. Okay, and then material balance of the gas tank. And here I have to use initial reservoir pressure. Be careful to use the correct one. Initial set. Initial set. Current set. Playing games with GF, and then recovery factor. Okay. Yes.
Previously on exercise 1, you did the opposite way, sort of. So you calculated the pressure, the reservoir pressure, using the previous set R, and not the opposite like you did now. Now you said you calculate the set R using the reservoir pressure from the previous point, but in the other exercise you calculated the reservoir pressure first and then the set after.
It should give you the same, right?
Should
I think,
okay.
because here we're calculating that set based on the previous pressure.
Yeah.
Okay, but
The last time you calculated the reservoir pressure based on the previous set.
based on this set.
Yeah. For the
Yeah.
set I.
And this pressure and this set was calculated with the previous.
No, it was calculated with her.
No, you cannot calculate with the current. Okay. Yeah, it should give you similar result, I think, if you do it one way or the other. Yeah, I think so. Yeah. Just to be consistent, let's change it with the set from the previous. And this set we calculate with this guy. Okay, complain a bit, and then this guy I calculate with this set. Yeah. How much did we get before? The same. Okay. So I don't think should be the thing. The point is that the set changed very slowly, so I can use the one from the previous. You decide. I think should give you a similar result. But just to be consistent, let's make it like that. So I calculate this guy based on this pressure, and this guy, then M PI, and then I have to block this. Set I have to block this. Set I have to keep this one without blocking, and recovery factor this guy. Am I getting similar numbers than what you get? Okay, and then I simply drag. I suggest you to fill these columns like this, and then you drag everything down. You shouldn't fill anything on this side. Okay, that's when you have the compressor. That's for the second task. Okay, and then you select all of that line, and then you simply drag it down. And I think it should be maybe in year 5. I think that's where you start having something happened. What is the problem?
It might be that some of the formulas that's doesn't. When I do this, sometimes the formulas doesn't sort of update.
Yeah, I think here it's automatic. So maybe we had. Can you check please your recovery factor? How much do you have for? Is it this number for year 1?
0.04.
Yeah, for year 2, 0.08.
Yep.
Okay, and then the template M. Is it recovery factor 0.06, 0.1,
Yep.
0.18?
Yep.
Okay, so then we have something else. It's using the initial pressure, the initial set, previous set, the current recovery factor.
I got the in year 6 that it was negative and not year 5.
Yeah, but the delta P, oh, might be. Okay, so we get here that we, at this year, we cannot produce any longer. Year 6, we cannot produce any longer this rate of 3 million, okay, from template M. So there are different ways. So how here we have to apply a network. Okay, here we have to solve some sort of a network, some equilibrium, because now the choke has to be fully open. So you think intuitively it tells you I have to change this rate, right, until I find here it will be exactly equal to 0. Yeah? Will that work? Yeah? And if you see at the network, okay, if you see at the, I closed it.
Did you press the recording?
Yeah, should be. Okay, so let's see what does it mean, okay? It's like before we had simply everything was defined. Okay, I had to solve no equations. Simply I fix the rates and then I just verify. Okay. Now at some point in this template that gives you a negative pressure. Okay, that means that now this has to be open. Now I have to solve the system of equations. Okay, but this one is still positive. This one I can still continue flowing that rate. Okay, so if you see, it's like this equation is fully defined in a way. Okay, but this part is not fully defined, and I have to find a way that the rate, you have flow equilibrium only in this branch. Okay, so if you see, let's say junction, if you choose your equilibrium point is the junction, the pressure seen from here has to be equal than the pressure seen from here. That means that the rate that I assume, I have to go all the way here, and then I have to come all the way here and see if they are the same. Why I'm not looking at this branch? Because that rate is fixed, right? And then also I have the choke. So you see that how is going to be if the pressure is fixed, right? How is going to be the wellhead pressure? Fixed, right? That doesn't change. Okay. Now this pressure will depend on the equilibrium of these two, right? Here I have a rate of 6.7, but I have another rate that I don't know that this guy is producing. That's what I want to find. Okay. So I assume a rate has to be less than 3.3. I go all the way to the junction, and then with that rate I come all the way here and I verify. Are they the same or not? No, and then assume a new rate, go all the way here, come all the way here, and compute, compare, and so forth. So why is that not affected by this system? And that's kind of the main question. Okay? It's not affected because you have this choke. Let's say here you have a different pressure. As long as that pressure is lower, when you take that pressure, you calculate counter current, you compute the template pressure. As long as this pressure is lower than that pressure, I'm okay. That doesn't play any role in my solving my system of equations. Okay? So that's why I can remove it completely out of the picture and then just simply solve this system. Okay? So you can do two things, right? We can either use that, okay, for those of you who are brave, okay, so you can try to use that to solve that network. Or what is the other option some of you have done? Okay, some of you that have said, now what if we just change this value and then to drive this one to 0? Will that work? Let's try, okay? And we can compare with the other group that I don't know what's that, so reset. So we want to change the rate We want to drive that value to 0. Okay, by changing the rate of the well, of M, of the template M. Okay. And now this value will be simply something I calculate, I impose. Okay, does that make sense still? Okay, let's go back from the beginning of the sheet. That is still going to be up to here, 108, right? That all of that still remains the same. Okay, now I come to the separator part. I have now this rate should be, actually no, there is an error. Okay, this now this field should be this number plus this number, right? It's no longer 10. I have a lower rate. Okay, so you see now it's not the, what is the delta P of the choke? It's not 0, so we have to repeat that calculation. Okay, so now I'm using the right field rate divided by 2 to calculate this tow head pressure. Now I'm moving back from the tow head to the template, and these two pressures should be the same because the choke is fully open. Then it's fulfilled that condition. And then I'm also moving from the tow head all the way to template L, which is here. And you see that the difference between these two gives you positive. That means that I have to adjust the choke instead of using, I have to adjust the choke to have exactly 40 bar delta P. Okay, so I can solve it on the same line, but be careful, I have to make some changes. I had to come here and I had to change the rate of the field. Okay, now I continue. Let's take it one more step. Was that the same that some others were solving it here? Was that the same number that you got? How do I solve it? Let's take it, here. How do I solve that problem here with this network solver? Let's assume we cannot do it in the reservoir simulator. We have to do it outside. How do we do that?
You take the current pressure, reservoir pressure.
Okay, the first step is you have to take out these two numbers, right? The current reservoir pressure. So you have to take that for this guy, and you want to take it also for this guy here. Yes?
Don't you have to change back to the, before you change it? Or is it the reservoir pressure change?
You should do it whenever you have, because you're assuming you're producing that value constant the previous year.
Yeah, we already changed the template rate. Will the pressure, no, it won't.
But I'm
Sorry.
changing the template rate in the year, okay? Not if I change it on the previous year, that will affect the result on the current. Okay, what else do I have to change?
PWS. The rate, it's going to be opposite, right? So the rate is going to tell you what the PWS.
Yes, so I can provide, now I can do it the other way, okay? The key of the template, L, how much was it? 6.7. Let's copy that number here. Okay, now I'm going to paste it. It's getting very messy. Q template. Okay, 6.7, that's an input. With that, I calculate the Q of the well. Will be simply this number divided by 4. Okay, and then with that rate, I can compute bottom hole pressure, PWF. That will be C, N, PR, and Q. Okay, and so this guy should be blue. And with that, I move all the way to the wellhead. Okay? And then I use exactly the same equation, tubing P2. That gives me 108, and that should be the same number that I have here. Wellhead pressure, 108. And I stop. I stop there. Now I go on the other one. This, I'm not sure about the rate, right? But I know that has to be lower than 3.3. Okay, so let's try a value 3.2, for example. Yeah, but we have to change this number. Okay, so let's use 120. Yeah, should be 3.3, right? So let's try 100 and.
Could you just solve now for the PWF?
Yeah. So let's use something between 90 bar, okay? Just to get an initial seed. So we have that pressure, okay? We have, and that's 71. That's the pressure we're not sure, okay? That will depend on the rate that I have. What can I say about the choke? The choke in this case is open, right? For template M. Therefore, these two are exactly the same. What happens with the choke here? It's closed, okay? So it's no longer an input, but it's something I have to calculate. So I just remove this guy here, and I just for now, let's take out this equation, okay? So now we have template M. I move from the wellhead to the template, okay? I'm moving from here to here. And then the next step is to move from here to here. Okay, so that's what is being done here. I move from the template all the way to the towhead, calculate line P2. Okay. Here I'm moving from the separator backwards, okay, to calculate P towhead. And this equation doesn't play anymore any role, okay, because the choke of the well in L are not fully open. So I just simply remove it, okay, or simply this will be basically, yeah, let's remove it for now. So now these are the two that you want it to be equal, okay, by changing the rate. Or by changing PWF. You want these two numbers to be exactly the same. Okay? And now you again run your solver saying the error should be 0 by changing. You only want to change one PWF, the other you know the rate is fixed. Okay? And we can maybe take that away. And that's the solution, 68, considering only equilibrium on this branch, okay? You have said this is your equilibrium point, and we are making from this side and from this side. They have to be the same, okay? But for the calculation of this pressure at the towhead, counter current, you are using the rate of this rate, which is fixed, okay? You are including that in the equation, okay? So I'm considering only, to make the equilibrium, only this branch. How do I calculate now the delta P of the choke? I have to move with that pressure backwards here. Okay, so I say the P towhead for 1 will be simply that. Okay, it's common for all of them, so it will be simply that. And the P of the template will be line P1 with the flow line of template L, with the P2 at the towhead, and with the rate of the template. Okay, very little. And then we say this, the choke will be this minus this. And now it's calculated, it's not. And it should give the same, okay, if I didn't make any mistake. Uh, 60, how much did we get? 40. And here we have 39.7, okay, the same. Yes?
What if the template L reach a position that is not
possible to produce into a closed choke which should be open?
Yeah, that's what we are going to do next. Now we are going to move now more into the future. Okay? But did you see both? You see now clearly which one is much easier than the other. Okay? But I suggest this one is more complex, but you should also try to understand that approach. Okay? Because it really, if you understand the most complicated, then you can deal with any case. Okay? Now we move down, okay, to the next time. And what do we have to do now for each time? Okay, now the choke is negative. I have again to change the rate of template M, okay, to drive it to 0. The other one should remain constant. Here the choke is 29, so it's getting close to being fully open. That will be this value of 0 by changing this guy. And because they are very close to each other, the rates, it converge very quickly without any complaint. Okay, if the rates were very different, if you're trying to use a very high or very low rate, maybe it will have some more problem converging. Now we have still everything is in good shape here. Yeah, so let's see, now will be 33. $34. Okay, and the rate is reducing gradually, and the delta P of the choke, something is happening here. Why here it increased? Very strange. Okay, reservoir pressure was 0, so that's why it was so easy to flow. Okay, it's very painful, but just to show you step by step, okay? I don't want to use any tricks and then you're all confused. Okay, just to show you step by step, we do it slowly. What happened with 34? I thought it was converged. Okay, but it means the rate of the field is going down with time, which has expected. And now I have 8. So in the next time step, I should be probably, it should go to negative. Okay, so let's do one more step. Okay, 60, then I solve once more. Okay, now this one is negative. That we know how to change, but now this one is negative. Okay? So how do we solve that problem? Okay, so one option is to do exactly the same that we have done before, right? Simply just changing the rate. Okay, you can change this rate, and now you will change that rate to make the choke 0. That's one option. Okay? So let's see if that, do we have to make any other change in the Excel sheet? Okay, we are calculating, giving this rate, calculate up to here, and then going back, calculating up to here. Okay, and now this rate is not anymore a function of the plateau, but it's simply the sum of the two templates. So I think it should work. Okay, I suspect. So let's try to use solver. You want to drive what? the choke, right? Should the sum of the choke, the two chokes, should be 0. So I have to create one more function. Let's create here error function, dp choke. And that will be what? Will be this guy squared plus this guy squared, right? Because if both of them are negative, but it can be that one becomes positive, one becomes negative, and I will have 0. Okay, so I want to add both like that. Okay, and then I use the solver. Solver, please drive that value to 0 or to a minimum by changing. You want to change this rate, right? And then, and which rate? The other rate. So to make both, I push Control to select both. And this rate. Okay, a comma or the semicolon appears, okay, depending on your language. And then I solve. Okay, and let's see if it makes sense. Delta P of the choke is 0. The rate has been reduced to 6.4, and the rate was reduced to 1.2. Okay? Now, how do I solve it here? Exactly the same way we have solved it initially. Okay? If you remember, we said now the two chokes are open. So I can go all the way to the junction, from here and just solve. Okay? Because everything is open choke. So we can do exactly the same way we have done at the beginning. Okay? That clear? More or less? Okay, so I suggest now, you can take a break if you want, but I suggest you look into the last part of that exercise. Okay, because I think there might be some confusion on that part. Okay, when you look at the second part, where you want to prolong the rate. Now you want the rate still to be 10 million. Okay, so you want to see what is the delta P of the compressor. Okay, so I just want you to think about that. And but first, were my numbers correct? Did you get something similar? Those of you who've already solved it? Yep. Okay. So just look at the second task. How do you do that? So when you reach the end of the plateau, okay, which is here, instead of reducing the rate of the wheel, you want to keep it, okay, but now you want to use a compressor, and for that you have to use this part here. Okay, from that point on you have to continue. I suggest you make for the delivery, you create a copy, okay, and then you click here data. That will be first task. Okay. And here will be data task 2. Okay. And then you simply erase the part where you change the rate, okay, and then you do the compressor part. So think of it how you are going to do that part, okay? You want to keep the two rates the same, and you want to add a compressor. The compressor will be at here, at the top. Okay? You see, I was too ambitious once more. We don't have time to go to the ESP. I was saying this part, this network, needs you to think, okay? That's the intention. Needs you to be confused and have to think about stuff, you know, for some time. So don't be stressed if you don't get it right away, but just try to understand on your own way. The pressure has to make sense. If you have no choke, when you see it from two different places, they should be the same. When you have a choke, then the choke has to be positive. Okay? So you have always to make sure that there is continuity of pressure in your stream. No matter where you look it, where you put the equilibrium point, it should make sense. Okay? If you have no choke, if you have the common point, so think about that when solving this exercise. Also, another comment was, as you saw now you can use just that sheet to compute everything for task 1. You don't need at all this sheet, only to calculate the initial equilibrium, okay? To calculate the initial splitting. But you don't need it anymore for any of the other points. And actually it's easier if you simply do everything here. But if you want to practice, if you want to go at one particular time, you should, if you want to practice, you can use it to solve that time, to calculate the rates on that time. Because here you have to do it in a different way. Okay? If you do it here, you're placing the equilibrium in the choke. And you want the choke to be 0, the delta P. If you do it here, you're making the equilibrium in the junction. Okay? And you want the junction to be the same if you see it from different places. So it's a different point. It's a different problem. But it helps you to practice. For delivery, don't worry. You can do everything simply using this one for task 1. I have added a new more question, which is task 1A, that if you see the production profile, when you compute it, it looks like that. That's for the field, that's for template L and template M. You see that the reason why the field starts to decline is because template M starts to decline. Okay? So you could change the splitting in a way, intuitively you think if you lower, what did we say about plateau? Lower plateau, longer duration. Okay? And you increase this one, okay, until you prolong, you try to stretch to prolong the plateau. So that's the next question you have. If you adjust this number, okay, and I will say just make it smaller, and this one make it higher, you can prolong the duration of the plateau just by playing with the wells, adjusting how much each reservoir is producing. Okay? Now, let's go a bit on the compressor part, which is the compressor is, that's why I wanted to give you that exercise. The compressor really makes you think, and it's going to test you if you really understand network or not. Okay? So the way we have now this for template L, and then we have this template M going to that tau head. Okay, so that's the tau head. And now we place a compressor in between. And you have now a pressure that I say discharge. We typically, for a rotating machine, we say suction and discharge. So that's the discharge of the machine. And then you have these two flow lines that go parallel, that they go all the way to the separator. Okay? So one thing to note, that pressure at the discharge, if I'm making this rate, I'm operating in plateau. The whole intention of the compressor is to keep it in plateau. So if this rate is constant, how is the pressure at the discharge of the compressor? Constant, right? This pressure is constant, this rate is constant, therefore this pressure should be constant. Line P1 is constant, doesn't change. Okay? Now, what will happen with time when, with time, this reservoir pressure is going down? Right? Okay? And we find the first problem when this choke, actually of template M, becomes negative. Right? So that's the first challenge we find. When the choke becomes negative, that means I reach fully open choke. Okay? Now, this one had no problem, right, at that point in time. So that's the first case. The first case is template M, choke in template M. That's what happens first, okay? Delta P choke of M becomes negative. Okay? But delta P choke of L is still positive. That means that I can still flow with this 6.7 through here, through there. Okay? So what I say is that I have to bring back the Q of the template M back to 3.3. Right? That's what I need to produce to compensate. Okay? So I come with that rate, I come all the way to the wellhead, but now I don't stop at the wellhead because now I have fully open choke. I move to the template and then I move to the towhead. Okay, assuming that I'm forcing to produce 3.3 from bottom hole to wellhead to template to towhead. I'm going to get some pressure. Okay, so in template M, move from PWF to PWH to P template to P towhead. Okay. And it says if I want to produce 3.3, that's the pressure the compressor has to create. Equilibrium tells you that. If that's open, I'm producing that rate, so that's the pressure I need. That's the pressure has to be there. Okay? And then you have to check, but I'm still producing from here. I'm still producing what is QL? The Q of template L is 6.7, right? Yes? Okay. So you can verify that PWH, okay, of template L, or that the delta P, let's say with P towhead, verify that delta P of the choke in L is positive. You have that pressure that you calculate that you need, okay? Then you can come with 6.7 all the way to wellhead, and then you can go co-current from towhead with that pressure that you need back to the template, and you verify. If it's positive, that means that I can produce that rate. What is the effect of the compressor when I lower the pressure here? What naturally this reservoir will tend to do? Produce more, right? Because I'm lowering that pressure. This was 6.7, and then it will tend to produce more. And there I have to be very careful. Maybe the reservoir engineer doesn't want that rate to go higher than 6.7 for some reason. Sand production, coning, all kind of issues. So he wants, you have to keep it at 6.7 if you put the compressor there. Okay? So that's why we have to be careful. Keep it in 6.7, but we have to verify that the choke, and then probably have to choke a bit. Okay? So that case is very simple. No equilibrium there. I simply have to take fixed 3.3, fully open choke, come here, and then verify that this delta P is positive. Finish. Okay? Now comes the second step, which is more complicated, and it's going to give you some headache. Okay? And here delta P of the choke of L is negative, and delta P of the choke of M is negative. That eventually will happen. Simply you cannot produce more. What to do in that case? Well, if you see the first system, okay, we have one system which is L, looks like that. One system looks like that. And here I have the P of the towhead. How, if I look at each system, okay, always for networks look at divide and conquer, okay? We are looking simply at that system first, of the system M, okay? If I change the towhead pressure, if I want to make a plot of P towhead versus the rate of the template, how is that curve going to look like? If I lower that pressure, right, I will get higher rate, right? So that curve probably looks something like this. Separately, I'm just changing that pressure until I get that curve. Okay? Then what happens if I look at this system? The template L. How does the curve look like? It's the same point in pressure, but the curve is different. Okay, because I have different number of wells and different properties. But the curve will look exactly the same. If I reduce that pressure, that means I can flow more. With open choke. Okay, these curves are with open choke. With open choke. So what is the problem I have to make? The pressure should be the same, right? And what else do I have to find? So P tau head 1, let's call it these two pressures. Tau head 1 is equal to tau head 2, right? But you have the other constraint that QTL plus QTM should be equal to 10 million, right? So one way I will solve this problem, I assume tau head for both, right? And I read the rates, and then I see, is the sum equal to 10? No, I assume another T, and so forth. Okay, so it's two different stages in the life of the field. One of them, only one well fails, and then it's very simple. Then I just have to compensate with the other template. Okay, and in the other, both fail, and then I have to make this curve. What happens with reservoir pressure with this curve? If reservoir pressure goes down, that curve simply also goes down. Okay, because now I have less pressure in the reservoir. That's PR1, and now I have PR2. Okay, so with reservoir pressure, I have to repeat the same calculation. And you see that the tau head will have to become, to keep the same rate, it has to be lower and lower and lower. Okay, until you see on the exercise, you have that the pressure at the suction of the compressor cannot be lower than 5 bar, and the pressure delta P cannot be more than 50. So that's why you have in your Excel sheet you have these rows. Okay, if this one at any point becomes bigger than 50, or if this one the suction is the tau head becomes lower than 5, you have to lower the rate. Okay, there is no other choice. Okay, so I think that's all I had to say. You have now exercise set 3. Maybe will be one more problem, but you have these two. One we have worked yesterday and today, and you have well advanced, and then we have this that we are going to discuss next week. Okay, before we finish, are there any questions? You should have many questions. Okay, this is not trivial.
What if the delta P for the P tau is so low before the second one goes to decline?
What is if the pressure?
The P tau pressure, that's what you're increasing, right? It's kind of, you get the in the first case, you get the delta P choke to be 0 for the.
In this first case here.
Yeah. So then you're taking the P tau and reducing it so that delta P choke for the M
Will be 0.
will be 0.
Mm-hmm.
But that drops really, really fast.
Yeah, but that's only for when you still can produce from L and just want to compensate from M. But eventually you will enter in both are going to be negative. No?
I didn't
You already solved it?
Yeah,
Okay.
try it, just doing it manually.
Yeah. If at some point that pressure just goes below 5, simply just open both chokes. Okay? But it should be, is it below 5?
No, but it's above 50. The difference.
The choke?
The compressor. Or,
Yeah. Okay. See you next week. Enjoy the weekend.